So welcome to lecture number 2 in the series on electrical machines. So looking at the course, we'll be starting with DC machines. So first of all, so as we talked about last time, DC machines, we can have actually DC motors as well as DC generators. So we'll be using DC source as a supply of electrical energy, or the electrical energy delivered will be in the form of a DC voltage. Fine. So most of the DC machines are like actually AC machines. They will have actually, constructionally speaking, they will have having the same features, and even the voltage that is actually induced in a DC machine in the armature actually is basically an AC voltage. But how we actually obtain then a DC voltage from that, we'll look into that. So if you have already if you know about something about rectifiers, uh, rectifiers basically convert AC voltage into DC voltage. So you might have studied about diode bridge rectifiers. So when you talk about rectifiers, we can convert AC voltage into DC voltage. This process is known as actually also known as a process of commutation. So in a similar manner, using certain arrangements, we can convert the AC voltage that's actually induced or generated in a DC machine into DC voltage. Fine. So the fundamental principle basically that's involved in the operation of a DC machine is very simple, and it's as stated using a simple conductor in a magnetic field. We can describe how voltage can be induced in case it's a DC generator, or how a torque will be induced in case it's a DC motor. So we'll be starting with the very simple arrangement that's of a simple rotating loop. Right. So this here basically is a simple DC simple rotating loop. So you can see there is a magnet represented by north and south poles. Fine. You can consider it as a permanent magnet right now, and there's a single wire that here is shown as coil turns A, B, C, and D. Fine. So this is single loop of coil that's placed within this magnetic field. This coil is a rectangular structure represented as ABCD. So when this coil is actually placed in the magnetic field, and if a current is made to flow through this coil, it will experience a torque and it will start rotating. So that will be the principle of a DC motor. And the same coil, if we rotate it by some mechanism within this magnetic field, a voltage will be induced in these coils, and we'll be able to obtain DC voltage by using proper arrangement from this set of coils. So the same machine can actually be used, same rotating loop, same single loop of coil placed in the magnetic field can be used as a motor as well as a generator. So this is a fairly simple case of a system wherein we have placed this is a linear case rather actually, wherein we have placed a single loop of coil, a single turn of coil in between magnet. So the real motor or a generator will actually look somewhat different from this, but this is we'll start with this single loop of coil to understand the behavior or to understand the operation using as to how a DC motor or a DC generator basically works. Fine. Also some of the terms will be introduced here that we are actually not familiar with. So here we have a rotating part, and this rotating part is referred to as a rotor. Fine. The rotating coil, whether it's for this linear machine or in for real machines, that's even if we are talking about AC machines, the rotating part will be referred to as a rotor. The stationary part, that's actually the magnets in this case, it's called the stator. So this is true for both AC machines as well as DC machines. You will have, physically speaking, two components. One will be the stationary part, that will be called as the stator, and another will be the rotating part, it will be called as the rotor. Fine. And in this particular case, you can see the stationary part is the magnet. It is responsible for production of field, so this part will be referred to as field also, while as the rotating part, in a short while you'll see that actually the induced voltage in this rotating part is an AC voltage. So this rotating part actually refers to as coil through which current is made to flow in case we want a motoring operation, or or if it's a generator, then the voltage is actually induced in this coil. So this uh, part is referred to as the armature. Fine. So mechanically speaking, every machine will have two components. One will be the stationary component, that is referred to as the stator. Another one will be the rotating component, that is called as the rotor. Or electrically speaking, they are actually represent two different circuits. One circuit is known as the field, another circuit is known as the armature. So field is actually responsible for production of the electromagnetic field, while as armature is the current carrying coil in a electrical machine. Fine. So this is actually true for all machines. This is not only the case of a. So this here basically refers to the simplest, most machine, or a simplest, most rotating form of electrical machine. Fine. So let's try to derive equation. Construction wise, this is simple. There is a magnet and there is a coil placed within this magnet. So if this is a ferromagnetic material, this coil is made to align with the magnet in a certain in a perpendicular direction. These magnets are referred to as a field. The coil is referred to as the armature. Also, this is the electrical definition. The mechanical definition is that the magnet is stationary, so it will be called as the stator. The coil is rotating, so it will be called as the rotor. So we have now a coil ABCD placed in a magnet, under the influence of a magnet. So the magnet will actually be producing a magnetic field. So next what we'll be doing is we'll try to derive the voltage induced in this rotating loop. So this will help us serve the purpose of deriving the equations for a DC motor or DC generator. Fine. So we have a coil ABCD. A, B, C, D. That's actually placed in the magnetic field, or this is a top wave. If we look at the front wave of this, you'll be actually having a coil A, You have a coil A, B, C, D that's placed in the magnetic field, and this coil is actually rotating. Fine, so this is rotating. So the principle of operation of a generator is that a rotating coil is placed in a magnetic field. So ABCD is actually rotating. So ends AB, you can say they are rotating. If it can either be a clockwise rotation or it can be an anti-clockwise rotation, depending upon the magnetic field. Whether say for example in this diagram we have north on the left side and south on the right side, so accordingly you can see the rotation will be depending upon the nature of induced voltage. Now we understand that if a single conductor is placed in a magnetic field, the induced voltage is V cross B dot L, that we have actually determined last time. So here we'll also make sure that we put this we have this coil whose length is L, since it is rectangular, so this is also L, and let us say this is 2R, where R is actually the radius of this coil, rotating coil. So what happens in this coil, we'll go segment wise. Let's take first of all look at segment AB. What is happening in the segment AB of this coil? So what happens in this segment is that the velocity of this wire is actually tangential to the path of rotation. So that means actually what happens is if we have, so what's exactly happening is you have a coil, at the front view you have a coil AB and you have a coil CD. The magnetic field is in this direction, B, fine. The coil is rotating, say in this direction, this is V, fine. So if we take the Fleming's right hand rule and we see and we represent the velocity, the magnetic field and the direction of current by the three fingers of by our three fingers using the right hand rule, we see that the direction of current will be into AB. That means current will actually be flowing from A to B. So if current is flowing from A to B, that means this end is positive, this end is negative. That means the induced voltage EAB is having this notations. The end A is positive, the end B is negative. So with this in mind, we have V cross B. V is actually the velocity is actually tangential to the path of rotation. So our cross product, that's actually V cross B in this case, will be in line with the tangential path, since induced voltage is given by V cross B dot L. this will be equal to VBL. Fine. So this is in segment AB. What happens is that the induced voltage will be equal to VBL, where L is the length of the segment, line segment AB. Then comes segment BC. If you look at the segment BC, in this case, half of the line segment, that's from B to, say for example, E, lies in under the influence of the south pole, whereas E to C lies under the influence of north pole. What happens is the induced voltage in this case is actually 0. In the first half of the segment, the quantity V cross B basically will point into the page, but in the second half of the segment, that's E to C, the quantity V cross B will point out of the page. So total, so that actually makes sure that the induced voltage in this line segment is actually 0. So I write here, this is EAB, this is EBC. EBC comes out to be equal to 0, since V cross B is actually perpendicular to the line segment L. Since V cross B is perpendicular to L, VBL cos of 90 means 0. Then comes the segment CD. So just like as in case of segment AB, in this case again the velocity of the wire will be actually tangential to the path of rotation. In this case you can say velocity V is in this direction. Looking at again using the Fleming's right hand rule, you will see that the direction of current in this case will be coming out of the page. That means current is actually flowing in this direction from C to D. So C will be positive, D will be negative. So ECD is a positive voltage, EDC is a negative voltage. So ECD again will be equal to VBL. As far as segment DA goes, again just like the segment BC, half of the line segment of DA will be under the influence of north pole, half of the line segment of DA will be under the influence of south pole. So the product V cross B is actually perpendicular to the line segment L, and therefore V cross B dot L, the dot product, is actually coming out to be 0. So EDA is again equal to 0. Now the total induced voltage therefore is given by EAB plus EBC plus ECD plus EDA, which is equal to VBL plus 0 plus VBL plus 0 VBL plus 0. Fine. So that's equal to 2 VBL. So we have a simple loop of wire A, B, C, D that is actually under the influence of a magnetic field. This is your north here, and this is your south, or at this end. The magnetic fields of lines are actually generated from north and they are terminating at the end south. Using the Fleming's right hand rule, what we'll be doing is actually Fleming's right hand rule, V cross B dot L. E induced is actually equal to V cross B dot L. We know this formula, E induced is V cross B dot L. So what we'll be doing is V will be represented by the thumb, B will be represented by the right index finger. Therefore, the middle finger will actually be referring to the direction of current. So if you properly see this, B is in this direction, fine. V is pointing in this direction. In that case, the right middle finger will actually be pointing into the plane of this page. Into the plane of the page will be referring all those currents that is actually into the plane of the page by a cross, whereas all those currents that will be represented by out of the page will be represented by a dot. ठीक है, तो जहाँ पे भी हमें करंट into the page दिखानी होगी, we'll be using the symbol cross. Wherever we'll be showing the current out of the page, we'll be using the symbol dot. So using the Fleming's right hand rule, knowing that V is giving the velocity is given by the thumb, B is given by the right index finger, and the right middle finger basically gives you the direction of current, or the direction in which the current in which your loop actually is, fine, along the length of the coil. So in case of segment AB, when it's actually under the influence of south pole, you will see EAB will be equal to VBL, fine, because V and B have an angle of 90 degrees with respect to each other, and V cross B have an angle of 0 degrees with respect to L. On the other hand, in the segment BC, BE is under the influence of south pole, EC is under the influence of north pole. So half of the segment is under the influence of south pole, half of the segment is under the influence of north pole. So all in all, what happens is, also because the line of the also the length of this conductor is actually perpendicular to V cross B. So V cross B dot product here means the angle between V cross B and L is 90 degrees. So cos of 90 will be actually 0. So EBC is 0. So similarly, we see that ECD is equal to VBL and EDA is equal to 0. So your total voltage for this case is equal to 2 VBL. Now this is true for 180 degree of rotation, fine. EAB can be under the influence of south pole for a period of 180 degrees, but EAB will be under the influence of north pole for another 180 degrees. When this loop is actually rotating, so for 180 degrees, the line segment EAB will be under the influence of south pole. For another 180 degrees, the line segment EAB will be under the influence of north pole. Now what happens is, after some time, after 180 degrees of rotation, now you have north here, you have south here, EAB has shifted to this side. This is your A, this is your B, this is your C, this is your D. So looking at this now, what you see is EDC will be equal to VBL for after 180 degrees of rotation. After 180 degree rotation of the coil, now EDC will be under the influence of south pole. So EDC will be equal to VBL, ECB will be equal to 0, EBA will be equal to VBL, and EAD will be equal to 0. So E total is equal to EAB plus EBC plus ECD plus EDA, fine. Here EAB, EBA is equal to VBL, that means EAB is equal to minus VBL, EBC is 0, EDC is VBL, that means ECD is equal to minus VBL. So this becomes minus 2 VBL. So what you can see is we can draw waveform. This is 2 VBL from 0 to 180 degrees. E total with respect to theta. You'll see this is theta of the rotor from 0 to pi. The voltage will be 2 VBL. From pi to 2 pi, the voltage will be equal to minus 2 VBL. So we are actually talking about a DC machine, but you can see AC voltage is actually induced in the coils, or you can say the armature of a DC machine. So this is a simple rotating loop wherein we have placed a coil ABCD under the influence of north and south pole using the Fleming's right hand rule. See the direction of current in each line segment. In the line segment, that's EBC and EDA. Since half of the coil will always be under the influence of north and south, the net resultant will be 0 voltage will be induced in EBC and EAD, whereas whatever is under the influence of south pole or north pole, that line segment, in both cases the induced voltage will be VBL. Now looking at the convention, what happens is that an alternating voltage is actually induced in the coil segment. So this is about the principle of operation of a simple rotating loop. Now we have actually obtained an AC voltage, but we need to obtain a DC voltage. So what we do is we use a brush. Fine. So what is the role of this brush? And actually it will be also associated with the commutator segment. This coil ABCD is rotating, but these brushes are kept constant. So if this brush is in contact with the coils ABCD, so they will be in contact, but they are not fixed to each other. That means even though the coil ABCD is rotating, they will not be twisted because they are not fixed to the brushes. They will only be touching these brushes. So the brushes are kept themselves constant. So always in the segment AB, the voltage that will be induced will have the same polarity, whether it's AB in this end or there is the coil segment DC is at this end. This brush segment will always carry the current that will be located, that will be flowing through this path. Fine. So this current will actually be either flowing through AB or it will be flowing through the coil segment DC, but whatever segment is at that end, the brush will only collect positive voltage or negative voltage, and this brush is also fixed at this end. Fine. So whether you have the coil segment DC at this end or you have the coil segment AB at this end, it will be carrying the same voltage under the influence of north pole. So as far as AB is concerned, the coil segment AB is concerned, it can be under the influence of south pole, it can be under the influence of north pole. So the voltage induced is positive or negative, but because of the brush segments that we are fixing here, brush and commutator segments, the output voltage will always be DC because this brush are fixed and they'll be carrying forward only one sort of current. So this is how we basically transform AC voltage that's actually induced in this coil into DC output voltage. So the output voltage actually, if we have drawn voltage like this, so the output voltage that actually will be that the brushes will actually obtain is something like this. Fine. So even though there will be some distortions, it will not be a purely DC, but since the frequency is very high, it will look as if it's constant voltage and we are obtaining a DC output voltage. Associated with this are a number of losses, brush losses, commutator losses, commutation problems. We'll be looking into those in detail when we study the DC machines. So this is about the induced voltage, the generator action of a simple rotating loop that emulates the performance of a DC machine. And you need to understand this, that the voltage induced in this rotating loop is itself AC, but because of the arrangement of commutator and brushes, we are able to obtain DC voltage from this arrangement. So this is a basic principle of operation of a DC generator. So we'll be extending this to real to actual generators, to actual DC generators, the concept of this simple rotating loop. We have derived the induced voltage. We need to derive the induced torque, that will actually be referring to the motoring mode of operation of this simple rotating loop. That will be doing in the next session.